without further ado, let's begin our new series on Lagrange Mechanics. We are on part 1, the calculus of variations. Again, my notes are available on Discord. You can either type !Discord if you are on Twitch, or you can find the Discord link in the description below for those of you who are watching on YouTube. We are going to be following Classical Mechanics by John R. Taylor, as well as using land down lit shit sometimes. Colin Dukes, welcome to the channel. Thank you for the follow. Let's see. How do we do this? Oh, I've lost it. Here we go. We're in the back. Now, we do have quite a few bits of notes today. As you see, this is one of the longer bits of notes, but I don't think we're going to, I think we're going to fly through them. But we have a very interesting friend of ours that we're going to find at the very end. If you guys stick around to the end, something very interesting is going to show up, which I was very excited to see when I was making my notes last night and this morning. Very cool stuff. So, we are on Lagrange Mechanics. Oh, I keep writing that. Mechanics. Mechanics. Part 1. Calculus of variations. All right. So we have to start our understanding of Lagrange mechanics by going back and doing something that we don't even need a Lagrange for yet. Okay, so the best way to understand and utilize the flexibility of the Lagrange equations is to use what we call a variational principle. Okay, so we're going to see 2 examples in our notes of what this variational methods are, these variational principles. We're going to talk about what they are and how they behave. And in order to understand them, we're going to start with a couple examples. So let's start with the first example. And this example is going to come back later in the, at the very end of the discussion today. We're going to actually solve this. We won't be solving it right off the bat. So how do we do that? So what's the first example? The first example is a shortest path between 2 points. So say we need to find the shortest path between 2 points. If you guys are following along the general relativity series on Friday, you know that this comes up all the time. We need to find the shortest distance between 2 points. So let's understand what that looks like. Again, similar to the path integration things that we had going on, we have a y and an x. We have a point right here that we'll call 1 that has a spot y1 and x1, and then a point back here and here called, let's see, where is that? I think it's right here, called 2 with y2 and x2. And then we'll have a line that connects them. Now we know that this line, we have a rule. We want to make sure, we want to find basically what line is the shortest line. So we'll call this y equals y of x. So how do we figure out if it's the smallest segment between 2 points?
Things get a little bit weird.
Actually, yeah, let's consider this point right here. And we'll call this some infinitesimally small point ds. So we're going to look at a small infinitesimal point and see how it's changing. I think that will tell us whether or not we can get to the shortest, whether or not we have the path that is the shortest distance between those 2 points. Now you might say, infinitesimal arc length, yeah, very good. You might say, that's a good way to put it too. And see, but soon we're going to need it to be,
the people need you.
Soon we're going to need it to be like the hypotenuse of a triangle too. So we'll find the arc length is more of like a straight line, but we'll get there soon. Now, now I think that everyone realizes that the obvious answer to this question, what is the shortest distance between 2 points, is a straight line, right? You've heard that many times. But do we know? Is there proof? So someone might say it's obvious. obviously. And we
Nothing
love
is
that
obvious.
in physics. We love that in physics. Yeah, exactly. Nothing's obvious. We love in physics. Some people might say, oh, it's obvious that it's a straight line.
Depends on the metric.
Is that expansion? Oh no, it's entropy. Straight line. But where's the proof? And you can check the pudding all you want. Trust me. I've been to the bottom of every pudding cup. And the proof is actually not in the pudding. Alrighty, so where's the proof? Do we have proof? So let's talk about this. Let's enhance, okay? So if we enhance that, we get some line segment here. We're gonna say this is a dx and a dy, because this whole thing is ds. This is dx, this is dy. So we have enhanced this small segment here and really honed in on this. And we said if it's a straight line, so if we have a short segment, so an infinitesimally short segment is going to have a straight line, and we want to just call it this, dx squared plus dy squared. So the point is to try to prove if this is the shortest line, right? Now that would definitely help us if we knew that. That way ds isn't changing from anything. It's going to be the shortest line would be the hypotenuse of this triangle. And it would have to be the same way across the whole entire path. And then we would find out whether or not it was, in fact, a straight line. So, how do we do that? Well, we're going to have to build up some mathematics so that we can understand it. I define straight such as the meaning changes in the metric so that the straight line between 2 points always corresponds to the geodesic. Sure, and we'll get into geodesics next week, I think. But yes, that's a very good way to state it. Let's get to the little mathematics. Let's try to unpack these a little bit. Let's try to understand what dy is a little bit. Now, this would be the mathematicians in chat will have a heyday with this, but this is physics, so we're gonna have some fun. So, boring math professor, if you're here, just turn away. Close your eyes. You don't want to see this. It's like from that movie Walk Hard or whatever. You don't want none of this math. So we're gonna do that little jaunt right there, right? And now we can redefine this as the derivative of y with respect to x, dx. All right, that's funny. So then the length of the path from 1 to 2 relies on our unknown. Oh wait, well, we have to do another step first. Hold on. Let's do the next step of that's putting it in here, and we can find out that ds, which is equal to the square root of ds squared plus dy squared, is then also subsequently equal to the square root of 1, plus y prime of x squared dx. And all I'm doing is taking this, there's a dx now for this dy, there's dx, so that's dx squared here as well, so I can factor out the dx squared. You take the square root of the dx squared, you get the dx on the outside. And inside you're only left with this 1 plus y prime of x squared. Now, that tells us that the length of the path from 1 to 2 relies on our unknown y prime of x.
Things get a little
or y of x.
weird.
All right, so now we see that if we want to do a minimization problem, right? Make it the shortest path is the goal here. So finding the shortest path turns into a slightly more complicated problem than just finding a minimum of x on f of x, right? Like we've done that several times. We're going to see that pretty soon again. You've done the calculus where you have to find a minimum value. Either way, I'm not too worried about it. Need to forget it all. Time for a nap. Nice. Let's do the following. Let's do the second example, okay? So this is the first example, and we're going to have to solve this eventually. And like I said, that's how we're going to end the stream. The goal right now is to figure out how to find the shortest path on this. So now we have our second example. When I started this shindig, I had no idea how many people were going to show up. Let's start the second example,
Welcome to the channel.
which is known
Things get
as
a little bit
Fermat's
weird.
principle. Beautiful, beautiful voice. This is similar to the last problem, except now we would like to find the shortest path, or we would like to find the path of a light beam, which we know should be the shortest one, right? So the shortest path of a light beam between 2 points. However, we have some more things to consider now, right? What if the refractive index of the medium is constant, then we're going to get the exact same problem as before, right? There's nothing changing that shortest distance of the light inside of the medium. So it's just going to be what we would expect to be a straight line, and we'll have to go through the rigor of proving that it's a straight line. However, if it's not in a medium with a constant refractive index, i.e. if it goes from one refractive index to another, then we're going to have something different happening. So can we talk about that as well? And we can, believe it or not. That is to say, if we want to talk about the time it takes for light to travel a short distance, ds. So if we want dt, we can find that to be ds divided by v. How does that make sense? Well, we'll just cross multiply. V is equal to ds over dt. Infinitesimal small time over infinitesimal small place. Infinitesimal small distance over infinitesimal small time equals v. What's v though? V being not the speed of light, but the speed of light divided by the index of refraction. Obviously, if the light's going to be refracted, if we're going to have a change in the path due to the index of refraction, we need to have a way to account for that. So that's where the n comes in. So this is expressed as we can talk about the time of travel. So let's talk about the time of travel, which is equal to our new integral. So we're going to be integrating from 1 to 2 of dt, knowing that if we integrate over that time, we can figure out the time of travel. Let's see here. So the time of travel is equal to the integral 1 to 2. So going from point 1 to point 2 of dt. We can then, of course, substitute our dt in. And what do we get? We get the integral from 1 to 2 of ds over v, right? And if we substitute in again now for our v to get rid of that, we can find out that this integral can become 1 over c times the integral from 1 to 2 of n ds. Okay? So now what we really care about is the n that varies. We want to talk about it's changing through an n. We want the most general, as you're going to see, the kind of like the theme to this is finding the most general formalizations. That way we can be very, encompassing of all of the ideas. We don't want to sit there and be like, well, let's just do it through an n that doesn't change and go back to the original problem. Well, we could, however, that's not going to be all encompassing. We're not going to have a good idea of every single situation. So we want to have very general cases. And this is a good general case, right? We can have the integral from 1 to 2, from point 1 to point 2, of some index of refraction that changes for x and y, times our infinitesimal small distance. And of course, as we found out, integrating that infinitesimal small distance will get us into the entire path. Now, we can also do the integral from x1 to x2. This is equal to the integral from x1 to x2 if we substitute in what our ds is. Now, like we said, we're at the point where we can go back and utilize what we did in the first example, because the only thing that's different is the fact that we have this index of refraction. We have isolated the index of refraction away from ds. Basically, it's already automatically isolated because of this. So we don't really need dx or ds to rely on n or anything like that. So we can substitute ds in, and we're back to the same thing. Now, if we said something like, hey, the index of refraction doesn't change in the material, this becomes a constant, comes back out here, and we're back to our original problem of trying to find the shortest path. Hi, Zoiku. Welcome, welcome, welcome. So what are we interested in? Well, we're interested in finding the minimal paths, right? So now we're away from the two examples. This was example 2. We will not be solving this one because we're going to be solving the first one, and then this is kind of redundant at that point. But what are we interested in? Well, we're interested in finding paths that make the integral stationary. What that means is if the integral or the path is stationary, then that is to say that infinitesimal deviations from the correct course won't change the integral. But we can say it in kind of easier ways than that. We're trying to figure out when the minimum and maximums are of these equations inside, right? That's what I meant. I want to increase my understanding of differential forms, thinking about adding some analysis study for funsies. I loved real analysis, but I don't know if I could do it anymore. The proofs are very rigorous, but they're a lot of fun. Ty does a lot of that, and so does Boring Math Professor. I think Boring Math Professor does that. Right now you're on algebras, so I think that's a little different. But I think you did analysis last term, right? Or over the summer, something like that. Maybe not. Maybe I'm thinking of something wrong. All right, but this is ultimately going to break down to something easily understandable, thinking about calculus, right? And that's finding minimums and maximums. So let me give you a little refresher, a little visual refresher. We can think about a function, f of x and x right here with a minimum x sub 0. Well, what does this tell us? How do we know it's a minimum? Well, we know it's a minimum if the second derivative with respect to x is positive. Now we know it's a minimum. These are back to our rules from calculus. Now, how about a maximum? Well, the same thing, f of x, a function of x and x with a maximum right here. And this is, we know it's a maximum when f double prime x is less than 0. And lastly, we have one more thing to be a little bit weary about, and that's, oops, that doesn't even look good. And that's when picture this is straight across, x sub 0, and we have f of x. And something happens when f of double prime of x is equal to 0. You can either have a minimum or a maximum, or it could be neither. And that would be something of curiousness to us as well. So we have these rules from calculus that we spend a lot of time understanding and looking at. Cool, so this is what we have for our second integral, and then also just a little refresher on what minimums and maximums are in calculus and how we find out whether or not they are minimums or maximums. So, let's keep going. That sounded like thunder, but it's bright sunny out, which causes me significant confusion. So this is to say, so again, we want to figure out a way to make the path that makes the integral stationary. That is to say that our infinitesimal deviations from the correct course don't change the integral, i.e. we want to make it minimize. The calculus of variations is exactly this. We are studying deviations from paths. So yeah, so that is what calculation of variations is understanding the variations of the paths inside of these integrals. And that's what our goal is to do. So let's take this integral in all its glory. We'll have some s, some distance s. And we'll go from the x1 to x2, which we know next week this will turn into the action. I think it's next week. And we'll have some random function whose variables are y prime of x, and x. This covers all of our grounds to have a full function that exists much similar to the ones we had before. So let's draw another picture to kind of get a good grip on this, and we'll have to add some stuff to it this time. So here we have our x1 and y1, and then the point that they connect. We'll have our y2 and x2, and then our point that they connect. And then we'll have some function or some path we'll call y of x. And we want this one to be the correct path. We'll call it correct path, though I think Taylor calls it right path. We didn't do that yet, Neuro, but I have a fun thing about that. Stay tuned. We won't be doing that today, actually, guys, but I have a fun thing about that. Okay, so we have the path here, but again, this is just our correct path. This is not general enough. This is just not general enough. Why? Because we want to talk about all the paths. Why do we want to talk about all the paths? Because we don't know the correct path. We need to find the correct path.
Things get a little bit weird.
Matt stuck in the moon goo. Welcome to the channel. Thank you for the follow. 996. So close. Now let's go here. So what do we do? So let's just draw another path here. And we'll call this the wrong path. Okay? We'll call this the wrong path because it's going to be the addition of some general thing. So we'll call this one the wrong path. This one's going to be big Y of x, which is going to equal a little y of x plus some other function. Okay? The other function being the thing that makes it different than our correct. So this one includes our correct one plus some change, something that we don't understand, something we need to figure out. Now, the general function clearly gives a larger value of s. Then this can be convenient, right? Because like it's definitely if y of x is the smallest, like that's our goal is to show that y of x is the smallest, then we can say that anything added to the smallest is going to be larger. That's an easy thing to say. So the general function can contain infinitely many choices for eta of x, but we want the eta of x. So there could be infinitely many of those, but eta of x equal to 0 is going to get what's going to get us to the correct path. So included in all of it, there is the correct path, and we need to think about that. But still, there's a little bit of an issue with that. So we have to add one more thing. But before we do, it should be worthwhile to know that this is point 1, this is point 2. So we do have a nice boundary condition. The boundary condition is the eta of x1 is equal to the eta of x2. And that's equal to 0. Why? Well, because at 1 and 2, we want y of x1 to be equal to y of x1, and then y of x2 to be equal to y of x2. So we have some nice boundary conditions. This has to be 0, okay? Which will come in handy in a little bit. So in order to be even more generalized, because we want, again, ultimately looking for the most generalized way to do it, we can introduce another parameter. So this is going to be our new function. This is going to be the thing that we have to understand, and we will do that. So we're going to introduce a parameter alpha that we have total control over. We can just change the parameter as it will, as it were, as it wants to be, and understand how the function is changing, this one, for any eta, how the function changes based off of our choice of alpha. So now we can redefine this. So we're going to redefine s to a function s of alpha. Let me write that a little cleaner. Alpha. Brilliant. So now, the correct curve, okay? So the correct curve is now achieved by setting alpha equal to 0. So now, for all of the infinitely many choices of eta that exist, 0 being one of them, but now we don't need to rely on having that 0. We can have a parameter that we can just set to 0, and that gets us the shortest. Okay? So now the goal is to unpack this parameter and see what happens. Like, is there something hidden inside this parameter that we haven't been seeing? So this is to say the following. If we require that S is going to be the minimum for the correct curve, then we know that S of A, or S of alpha, excuse me, is equal to the minimum when, back to calculus, this is the fun part, we're going all the way back to calculus, ds of d alpha is equal to 0. So this is the minimum when this is equal to 0, but also when alpha is equal to 0. That gets us back to the y of x. So now we have two conditions. The derivative is going to be 0, that's going to be a minimum, but also alpha is going to be equal to 0 because that gets rid of this extra eta function. Oh, and it's raining again, so I guess that thunder made sense. And I hung up my blanket too. But either way, so that's the goal, is now we have to find this. So unpack, so our new goal, unpack alpha and solve ds over d alpha equal to 0. So let's erase this. The next part is going to be a little bit rigorous, so it's going to be fun. Hopefully we get it all in one board. Should I leave the picture? Yeah, let's leave the picture too. I bet you I can leave the picture. All right, so here we go. Let's unpack it. We have the function s of alpha, which is equal to the integral from x1 to x2 of f of big Y prime x dx. We know, let's make this a little bit bigger, that that's also f of little y plus alpha eta y prime plus alpha eta prime x dx. Okay? And so now we can evaluate our integral. So this is our derivative, excuse me. So this is ds of alpha. So ds of d alpha with respect to alpha is going to equal the integral from x1 to x2 of this partial of f with respect to alpha dx. So now we have a new thing to evaluate, this. Let's evaluate that as an aside. And then we'll come back and visit this again. So let's evaluate that down here. What is that derivative? Well, we have the full derivative. Let me rewrite the whole thing. The partial of f with y plus alpha eta y prime plus alpha eta prime x, all with respect to the partial of alpha. Now we have a little bit of an issue here. Let me write this cleaner. And that is, we don't really understand what this is, but we know the chain rule. Remember the chain rule? Let me refresh your memory on the chain rule. If we have dz with respect to dx, we can rewrite that as dz divided by dy times dy divided by dx. Okay? So if we were to apply that to this, what would the result be? Well, this is the result. Eta df dy plus eta prime df prime dy prime. No, not df prime, sorry, df dy prime. So that's the new, this is our new thing right here. So now we can go back to here because now we know what this is. We have that down, and we can write that. This isn't as bad as a partial as it looks. You can take the partial with respect to big Y. It turns out the d of big Y is equal to d of little y, so that's just a straightforward substitution. But if you were to take the partial with respect to dy, this first term goes to oh, I'm sorry, with alpha, excuse me, because we have dy over d alpha. So this one goes to 0, and this one goes to eta, and that's where this eta goes, and then you get this df of dy from there. So it is a pretty straightforward chain rule to do, but if you do have any issues doing it, let me know, and we can do it a little cleaner. But either way, so let's continue on, and we can do it at the end if you guys would like to see it written out. But dx1 to dx2, eta df dy plus eta prime df dy prime. Let's erase some of this so I can have some room to write here. There you go. So, ouch. And then, of course, this whole thing has to be equal to 0. That's the goal, is to get this whole thing equal to 0. Now, we do have a little bit of an issue here, right? Namely, in those eta primes. I think I go back and forth between the n and the eta, so apologize for that. But we do have a little issue with those eta primes there. Does that eta prime really, mean anything to us? Well, we have to figure it out. Turns out, we can actually do integration by parts. Integration by parts, the integral of u dv is equal to uv minus the integral of v du. You guys remember integration by parts? So let's take a look at just this one. Eta prime of x. The partial of f with respect to the partial of y prime dx. So we're just taking a look at this term right here. Okay? That's it. Just that. We can rewrite this, or we can set it equal to. How big is this? This is pretty big. I think we can fit it there. So if we actually were going to do a little bit of a trickery thing here, right? If we have the integral of u d, what is it, dv? Yeah, dv is equal to uv minus the integral of v du. Here's the trick. We're just going to take this and add it to both sides and add this to both sides and subtract this to both sides. That way we get the integral of v du is equal to uv minus the integral of u dv. So we're going to do a little trickery. Nothing major, but a little bit of trickery. And what are we going to get? I got to erase this so I have room to write. We're going to get that this is equal to so if this is our v and this is our du, then we'll get eta of x partial of f partial of y prime evaluated at x1, x2. Notice that if you evaluate this at x1 and x2, this is 0. So this term's going to go away. Minus the integral from x1 to x2 of eta x dx times the partial of f with respect to the partial of y prime times dx. We did fit it, just barely, but we did fit it. So this, like I said, is going to go to 0. So then the only thing we get is this is equal to this. Well, minus that. Cool? Cool? Cool. Now, let's do that substitution. What happens if we set this is equal to this and we put it in there? We get the following. What do I have? Oh yeah, ds d alpha is equal to the integral from x1 to x2 of eta x. Let's erase this. Let's go up here. There we go. Eta x times. We're going to factor out the eta x in each of these. The partial of f with respect to the partial of y minus the derivative with respect to x times the partial of f with the partial of y prime. And this dx. And this is equal to 0. Does anyone know what this is? That's the big one. That's the kicker. All of this was to get here. Why? Because if s is the smallest, if it's the minimum value, we need it to be equal to 0. How do we know it's equal to 0? Well, we already said we can let eta be infinitesimally whatever. It can be infinite amount of solutions. That doesn't help us. We need this a parameter to be 0. So if a is 0 and ds of dA is 0, then we know that it's the minimum thing. Admiral entropy is right. This right here, this is the famous Euler and Lagrange equations. So they naturally fall out of this if we are to start with the premise that there is one path that is the smallest path, and we want to find that smallest path. And soon you're going to see how important this is for the Lagrangian. That's what we're going to do next week. There is this very, very, very important thing that comes out of the equations. And that's what we do for next week. But before we finish up, let's go back to our original example and figure out how important this is in that original example. Okay? So this is the derivation for the Euler Lagrange equations. It is absolutely remarkable how cool that is, that just naturally falls out of this equation. And now we can sort of get to a prescription of the problem, right? The prescription of the problem being, how do we evaluate that integral? How do we find the minimum of that integral? And the prescription is 1. Set up the problem so that we get this integral. S is equal to the integral of x1 to x2 of f, the function of y of x, y prime of x, and x dx. Write down the Euler Lagrange equations in terms of our new f of y prime, and x. And then 3, solve the differential equation. So remember our original task. The first example. Some path comes from 1 to 2. Right? We wanted to figure out what that was. So let's try to solve it. The length is going to be equal to the integral from 1 to 2 of ds, our infinitesimal small part that we're going to integrate to the whole thing. This we found out is equal to, running from x1 to x2, of the square root of 1 plus y prime squared dx. Okay? So first we have to set up our integral. There's our integral. Nice. Now we got to figure out what is our f. Okay? So, and that's still part of the first one, is we write our integral, figure out what the f is, right? The f of y prime x is equal to 1 plus y prime squared to the 1/2. Okay? So this is the format. Inside that, the only thing we have is that as our function. Okay? Next thing is to find the components of the Euler Lagrange equation. Let me remind you what that equation is. Euler Lagrange equation. It is the partial of f with respect to y minus d dx partial of f with respect to y prime, which is equal to 0. This is the Euler Lagrange equation. So what are these each pieces, right? What's partial of f with respect to partial of y? Well, there's no y in there, right? So that's 0. What's the partial of f with respect to y prime? Well, there is a y prime in there, so we can take the derivative, and we'll end up getting y prime divided by, and then it's just the derivative of the inside times the derivative of the whole thing. The derivative of the whole thing being 1 over 1 plus y prime squared to the 1/2. So now if we set this equal, if we set these in here, we get 0 minus d dx of y prime 1 plus y prime squared. That music is rather distracting.
Hydrate, you fool.
Thank you, NC. And Tyrion. Thank you, Tyrion, for the cash in. Thank you, NC, for the attention grab. I appreciate that. Need that too. So now, and we are almost done.
Welcome to the channel.
This is equal to 0.
A little bit weird.
Unlimited Skies, welcome to the channel. Thank you for the follow. Good to have you, as well as everybody else. Okay, so where are we at now? So this is where we're at. Now, if you take the derivative of something and it's 0, what is that something equal to? Well, this something has to be equal to a constant. Y prime squared to the 1/2. The derivative of a constant is 0, so therefore that must be a constant. Let's rearrange this to find that y prime squared is equal to c times 1 plus y prime squared to the 1. Oh no, that's it. Because we're going to square both sides, blah, blah, blah. We're going to get that like that. We're going to do some more rearranging. And we'll find that y prime squared is equal to some constant we'll call m squared. Not for any particular reason. There's a particular reason. There is a particular reason, I swear. Let's take the square root of both sides. Y prime is equal to m. Y prime is, of course, the derivative of y. False, you differentiate functions, not numbers. Fair. Fair point. So what is the derivative of a function without a variable? Okay, so if y prime is the derivative with respect to x, can we integrate it to get to y? Of course we can. And we find that y is equal to mx plus b. Is chat in the way? Chat, you're right in the way. Y equals mx plus b. What is mx plus b? Sorry, you should be. I told you guys. Look out when I'm doing stuff. What is y equals mx plus b? It's a straight line. We've done it.